When you go into a plant, you enter a world of components, systems, processes, and variables. One of your first jobs will be to find your way around. To do this, you'll need to trace piping, pneumatic and electrical lines to find out how systems and instrumentation are interconnected. At first, this may seem like an endless job. Piping goes in all directions, and any component could have several instruments associated with it. But there is information available to help you find your way. This information is found on system prints, called piping and instrumentation drawings, or simply P&IDs. But using P&IDs puts you into an equally complex situation. You feel like you've entered a new world, a world of symbols, numbers, letters, and legends. Practically every plant has a collection of P&IDs like these that use symbols to indicate how the plant systems are connected and what instrumentation is provided with each system. The purpose of this unit is to show you how the instrumentation that we've covered so far is represented on piping and instrumentation drawings, or, as we'll call them, P&IDs. We'll begin by showing you how to use the P&ID legend. We'll also cover some of the most common symbols and letter designations used to identify instrumentation. And we'll apply all of this to actual plant instrumentation. Finally, we'll look at the 6 elements of control, and we'll see how they're indicated on P&IDs. Let's begin by covering some of the most common uses of P&IDs. Initially, they're used by people who build the plant. They're also used by engineers to evaluate the operation of systems and to make modifications when necessary. As an operator, you'll use them to trace systems and to find out how each system is laid out, as well as where components are located. P&IDs also tell you what instrumentation is installed for each system and where it's located, and you'll find P&IDs a valuable tool for daily operation. When you look at a P&ID, you don't see the actual equipment. Instead, you see symbols which represent the equipment. For example, this line represents a pipe where flow is being measured. This is the symbol for an orifice. This plain circle represents a locally mounted instrument, while this circle, with a line dividing it in half, indicates a remote instrument. The FT inside the local instrument tells us it's a flow transmitter. The FR inside the remote instrument tells us it's a flow recorder. The line connecting the flow transmitter with the flow recorder has a hash mark on it. This tells us that it's a pneumatic line. Now, there are many different symbol systems. Another system, different than the one we've shown, might show the same information this way. Once again, this line represents a pipe, and this symbol represents an orifice. In this case, however, the circle means a local indicator, while the rectangle means a remote indicator. Now that you know that there are a variety of symbol systems to choose from, you may be wondering how you'll ever make sense out of your plant's P&IDs. Well, the key to understanding the meaning of all the symbols and designations used on any P&ID is the legend. This is what a typical legend looks like. Like symbol systems, legends differ from plant to plant, and sometimes from print to print. But in general, most legends tell you at least 5 things: instrumentation symbols, identification letters, instrument line symbols, sensor symbols, and other miscellaneous symbols that are used. The first step in reading a legend is to look at the instrument symbols. In the system we're going to use, remember, your plant symbols may be different. The instrumentation symbols look like this. A plain circle indicates a locally mounted instrument. A circle with a horizontal line through it means that the instrument is remote. Now, while symbol systems and legends vary, in most cases a standard system is used for all P&IDs in a plant. For our purposes, throughout the remainder of this unit, we'll use this system to indicate instrumentation symbols. Now, there are a lot more things that you need to know about P&IDs, symbols, and legends. In the next segment, we'll look at some typical symbols and letter designations. For now, though, let's review what you've learned. First, you learned that symbols are used on plant prints to indicate systems and instruments. You also learned that the key to understanding the meaning of the symbols on a print is the legend, which identifies instrumentation symbols, identification letters, instrument line symbols, sensor symbols, and other miscellaneous symbols that are used. We'll stop here so that you can review the information in your text and answer the questions. If you have any problems understanding the material, ask your instructor to help you. As you know, if you're going to properly use the information contained on P&IDs, you first have to understand how to use the legend. At first glance, even a simplified legend like this may seem complicated and confusing. But by taking the information one section at a time, it becomes easier and easier to understand. We've already looked at this section of the legend, the instrumentation symbols. From it, you know that the symbol system for this P&ID uses circles. For example, a plain circle indicates a locally mounted instrument, and a circle with a solid line through it means a remotely mounted instrument. Of course, knowing where an instrument is mounted doesn't help you much if you don't know what the instrument does, how it works, and how it functions in the instrumentation system. To find this information, you need to look at the letters that appear inside the instrument symbol. The type and function of instrumentation is usually identified by at least two letters. The meanings of each letter depends on its position within the circle. In general, the first letter indicates the variable being measured. The second letter identifies the type of instrument being used or its function. A third, or sometimes fourth letter is used to identify additional functions that the instrument serves. The identification letters are explained in this section of the P&ID legend. If we take the letter T as an example, we see that when T is in the first position, it indicates that the instrument measures temperature. In the second, third, or fourth position, T means that the instrument is a transmitter. Let's look at an example to see how this works. This thermocouple on a feed water pump measures bearing temperature. The thermocouple transmits an electronic signal to this recorder for remote indication in the control room. On a P&ID, the pump and thermocouple could be shown this way. This symbol indicates a pump. This plain circle shows that the instrument is mounted locally. The T in the first position means that temperature is being measured. The E in the second position means that this is a sensing element. The recorder in the control room is symbolized this way, using a circle with a solid line through it. The solid line means it's remotely located. As before, the T in the first position means that the instrument is measuring temperature. The meaning of the R in the second position is explained on the legend. Here, you can see that R in the second position means that the instrument is a recorder. A typical example of a letter that is used in either the second or third position is A, an alarm function. If this recorder has an alarm function, for example, then the letter A would be placed in the third position, making it a TRA. On some P&IDs, an additional letter may also follow the alarm indication. The letters most commonly used are L, meaning low, and H, meaning high. These markings, like all other markings that appear on a P&ID, are explained in the legend. Again, using our recorder as an example, if the alarm on the recorder sounded when temperature got too high, then the fourth letter would be H, signifying a high temperature alarm. The recorder would be designated as a TRAH. If, on the other hand, the recorder is connected to an alarm that sounds when temperature gets too low, then the fourth letter would be an L, making the designation TRAL. Now, we've had to move back and forth from the legend to the instrument symbols on the P&ID several times during the past few minutes to identify the variable being measured and the function of the instrument being used. Until you've memorized the legend, you will have to keep it handy to ensure that you understand exactly what the P&ID symbols and designations mean. The instrumentation on the feed water pump that we've been looking at includes more than just one instrument. In addition to the thermocouple we've discussed, there is also a bimetallic thermometer. So far, the instrument symbols we've shown you have made no distinction between different instruments. But when there is more than one instrument, some system is needed to identify a specific instrument. On most P&IDs, there is a second set of identification markings that appear in the lower half of the instrument symbol. These markings include the instrument number and the unit designation. In our example of the thermocouple, it is on unit number 2 and is identified as instrument number 3A. On other P&IDs, only the instrument number or only the unit number may appear. To be sure that you know which instrument is which, you must become familiar with the identification system used in your plant. Now that we've seen the instrument symbols and letter designations placed inside the symbols, let's look at the lines that connect the various instrument symbols. The meaning of these symbols is found in the line symbol section of the legend. Two of the most common lines that are used on P&IDs are the broken line, which indicates an electrical connection, and the solid line with hash marks over it that indicates a pneumatic connection. Other lines that are commonly used include capillary tubing, which is indicated by a solid line with X's on it, and a hydraulic line, shown here by a solid line with L's on it. We've only shown you a few examples of the many different line connections that are used on P&IDs. If you ever have trouble identifying a line or any other symbol for that matter, consult your legend. Instrument symbols, identification letters, and line symbols are very important parts of piping and instrumentation drawings. Without them, you'll have a difficult time determining how the instrumentation on any system works. In the next segment, we'll look at sensor symbols and other miscellaneous symbols that are used on P&IDs. Then, we'll show you how some of the instruments that you've looked at in other units appear on P&IDs. For now, though, read the material in your text and answer the questions. Now that you have a basic understanding of instrumentation symbols, identification letters, and line symbols, we can begin to apply some of this knowledge to a few of the instruments that we've discussed in earlier units. At the beginning of this topic, we looked at a pressure indicating transmitter. You've probably already figured out where its nickname, P-I-T, came from. That's right, from its P and ID identification letters. This is what the symbol for a pressure indicating transmitter looks like. This plain circle means that the instrument is mounted locally. The P in the first position means that it's measuring pressure. The I lets us know that the pressure being measured is also indicated locally. The T in the third position indicates that in addition to local indication, this instrument is also transmitting a signal for remote indication. These circles with the horizontal lines through them are the instruments that receive the signal from the transmitter. The horizontal line through each circle means that the instruments are in remote locations. This instrument is a pressure recorder, indicated by the letters PR in the upper half of the symbol. The actual recorder looks like this. This instrument is a remote pressure indicator. It's identified by the letters PI. This gauge is the actual indicator that is used. It's mounted on a panel in the control room. Returning once again to the P&ID, you should also notice that an instrument number is indicated in the lower half of each instrument symbol. In this case, the instrument group or string is identified by the designation 1-61D. One final thing that you should know by looking at this diagram is that the instrument system is pneumatic. You know this because the lines connecting the instrument string together have hash marks through them. Let's take a look at another instrument system. This is an electronic transmitter with a sensor that measures the amount of oxygen in the flue gas. Notice that this transmitter has local indication. The transmitter sends an electric signal that operates this recorder. The recorder makes a permanent record of the amount of oxygen in the flue gas. Here's how it all looks on a P&ID. The AIT in the upper half of the symbol means an analysis indicating transmitter. The chemical that's analyzed is placed next to the instrument symbol. In this case, the chemical is O2, or oxygen. The remote recorder that is fed by the transmitter is shown here. The AR means analysis recorder. The broken line connecting the two symbols indicates that the signal being sent is electrical. This transmitter and recorder are both part of instrument string 2-6A, as shown by the letter and number in the bottom half of the symbol. Now, in addition to instrument symbols, identification letters, and line symbols, a legend also includes sensor symbols and miscellaneous symbols. These may not be found on every drawing, but we'll look at them briefly so you'll have some idea of how they're used. We'll use them in more detail when we apply this information to an actual print. The sensor symbols include such things as venturis, float devices, filled thermal systems, and thermometers. For each sensor used in an instrument system, there is usually a corresponding symbol. Here, for example, is a gauge glass used to indicate level in a storage tank. The L means that level is indicated, and the G means that the instrument being used is a gauge. This gauge glass is part of instrument group or string 2-8. By now, you should recognize that this instrument is indicating level locally. because it is symbolized by a plain circle. Similar symbols are used to show other types of sensors. Here is the sensor symbol for a filled thermal system used to sense the temperature of steam. The TE in this circle indicates a temperature element, and the TI in the second circle identifies a local temperature indicator. The line connecting the local indicator to the sensing element is capillary tubing, which is shown by a solid line with small X's on it. Miscellaneous symbols are the final symbols that we need to know about. These are symbols for instruments and components that don't easily fit into the categories we've looked at so far. Pilot lights, interlocks, purge or flushing devices, and board-mounted patch boards are just a few examples of miscellaneous symbols. In a little while, we'll look at a simplified P&ID, and we'll see how miscellaneous symbols are used. Keep in mind that what you've learned in this segment is just the start. You still have more to learn. But we'll stop here so that you can review the material in the text and answer the questions at the end of the segment. If you have any questions about the legend or the symbols used on prints, clear them up with your instructor before going on. What we've looked at so far are the symbols and designations for instruments as they appear on P&IDs. We've talked about the importance of reading and understanding legends, and we've shown you how these symbols are related to the actual components they represent. Now that we've laid the groundwork, let's take an example of a typical system as it appears on a simplified P&ID and see how the information that we've covered is used by operators. This is the system that we'll be discussing. You may recognize it as a condensate system. Right now, there are no instrument symbols on this P&ID. We'll add them as we go along. As we talk about this system, there are a couple of things you need to keep in mind. First, our purpose in this segment is to teach you how instrumentation is shown on a P&ID. Since we're not trying to teach you everything you need to know about the condensate system, we've simplified the P&ID considerably. The P&IDs that you use in your plant will undoubtedly be more complex than ours. The second thing that you should keep in mind is that all of the systems that make up a unit couldn't possibly fit on one page of a P&ID. Usually, one page of a P&ID will show all or part of just one of the many systems that make up a unit. So that you can identify which page goes with each system, P&IDs are usually titled and numbered. The title and number frequently appear in the bottom right-hand corner. The title and number are sometimes used to tell you where one P&ID connects to another. Here, for example, is where the turbine connects to the condenser. Since the turbine is not part of the condensate system, there's a note or tag that tells you the P&ID to look at if you need to see how the turbine and condenser are connected. In this case, the tag says, for continuation, see 9861-M. This means that for a continuation of this system, you need to consult P&ID number 9861-M. The actual words may vary, so you'll need to become familiar with the system used in your plant. Now that you know how P&IDs are identified, let's focus on this one. We'll begin by identifying all of the major components in the condensate system, and then go back and add the instrumentation necessary to make the system work. You'll soon see how complicated P&IDs can become, but if you treat them like we did the legend and approach them one section at a time, they're much easier to understand. The condensate system starts at the condenser. Steam entering the condenser is condensed, and the condensate collects in the hot well at the bottom of the condenser. A condensate pump draws condensate from the hot well and sends it through the gland steam condenser. From the gland steam condenser, the condensate passes through the condensate polishing system, which purifies the water. Then, the water is sent through the 7th and 5th stage heaters. From the heaters, the condensate goes through the deaerator, where oxygen in the water is removed to prevent corrosion of the system. From the deaerator, the water flows into the feed water storage tank. Finally, a feed water pump draws water from the feed water storage tank and sends it through the feed water system to the boiler. Now, the point where the condensate system ends and the feed water system begins varies. The P&ID you use will tell you how your plant's designed. Ideally, these are all of the components necessary to operate a condensate system and to maintain the steam cycle so that the amount of steam coming into the condenser is equal to the amount of water going out of the system. However, as you know, the water level in the condenser changes. For example, water level may increase due to a load change or decrease because of leakage. So, one additional component is necessary: the condensate storage tank. The condensate storage tank stores water and supplies it to the condenser when level is too low. We'll talk more about this system in a moment, but first, let's see what instrumentation a typical condensate system needs in order to work. We know that water level in the condenser hot well is an important consideration. Too high a level could cause turbine damage. Too low a level could cause a problem with the condensate pump suction. So, we'll use a transmitter to indicate condensate level locally, to initiate both high and low level alarms, and to indicate level remotely. The plain circle means that this transmitter is locally mounted. The letters LICT indicate that it is a level indicating control transmitter. We know that this is a pneumatic transmitter because the lines connecting the transmitter to the other instruments have hash marks through them. The legend identifies lines like these as pneumatic tubing. The transmitter is connected to a high level and a low level alarm. LAL identifies this as level alarm low, and LAH identifies this one as level alarm high. Since the circle symbols have lines through them, we know that the alarms are remotely mounted. We also need a remote level indicator so that condenser level can be monitored in the control room. This is the symbol for a remotely mounted level indicator. Notice that each instrument is marked to indicate that it is connected to Unit 1 and is part of Instrument Group 1. Another place where we need level indication is the feed water storage tank. Knowing the level in this tank helps you determine if flow in the system is balanced. By comparing level in the condenser hot well with level in the feed water storage tank, we can tell if the amount of water leaving the hot well is equal to the amount of water going into the feed water system. In our example, there is a gauge glass which gives local indication of level in the feed water storage tank. LG identifies this as a level gauge. There's also a transmitter, a high-level alarm, and a low-level alarm. Connected to the level transmitter is an interlock system to protect the feed water pump. The interlock system is indicated by broken lines and an interlock symbol which is diamond-shaped. This interlock system prevents the feed water pump from being run when the storage tank level is low. Next, we need to know the temperatures of the condensate going through the condensate system. This is measured in two places. First, it's measured at the outlet of the hot well. It's a locally mounted instrument. You know this because of the plain circle. And it's connected to Unit 1 and is part of Instrument Group 3. The other place temperature is measured is at the outlet of the feedwater storage tank. It's also locally mounted and is on Unit 1. It's part of Instrument Group 4. Pressure is a third variable that we need to measure. A condensate system is designed to operate under certain pressures. If the pressures aren't maintained, the efficiency of the unit will decrease and possibly cause damage to the components. On this P&ID, pressure is measured at the discharge of the condensate pump. This symbol, as you know, indicates that the pressure indicating instrument is locally mounted. Pressure is also measured at both the suction and discharge of the feedwater pump. Notice that at the suction of the pump, pressure is measured and indicated locally, while at the discharge of the pump, pressure is indicated locally on a PIT, as well as remotely in the control room. Flow is another variable that needs to be monitored so that it can be controlled. One place where we monitor flow is at the outlet of the fifth stage heater. It's a locally mounted instrument that's identified with the numbers 1-8. So, we know it's on Unit 1 and is part of Instrument Group 8. The second place flow is measured is at the outlet of the feedwater pump. This instrumentation consists of a transmitter, a remote indicator, 1-9, and a remote recorder, 1-9. All of these are on Unit 1 and part of Instrument Group 9. As you've no doubt realized, our P&ID is getting more and more complicated as we go along. But remember, this is a simplified drawing. The P&ID for your plant's condensate system will have even more symbols than these. Now that you have an understanding of the basic instrumentation that is needed to make a system work, let's talk a little bit about the primary purpose for having instrumentation: control. Ideally, if nothing ever changed within the system, control would be unnecessary. But as you know, water level in the condensate system fluctuates for a variety of reasons. Control is necessary to keep the fluctuations from getting out of hand. Let's look at a typical hot well level control system. This is what the hot well level control system looks like on our simplified P&ID. The system contains a makeup water line running from the condensate storage tank to the condenser. Flow through this line is controlled by this control valve, identified as LCV 1A. The LCV stands for Level Control Valve, and the number 1A identifies the specific valve. A second line, the dump line or draw-off line, connects the discharge side of the condensate pump with the condensate storage tank. A valve in this line controls flow and is identified as Level Control Valve 1B. In order to see how this system works, we need to look at this simplified diagram that shows levels and valve positions. Here's the condensate storage tank, the dump line and valve, the condenser, the hot well, the level indicating control transmitter, the high hot well level alarm, the low level alarm, the makeup line, and the makeup valve. This arrow represents the signal from the level indicating control transmitter. If level in the hot well drops, a decreasing signal from the level indicating control transmitter is sent to level control valve 1A in the makeup water line. The decreasing signal causes the control valve to open. Water from the condensate storage tank flows into the condenser. Level in the condenser should increase, but if level continues to decrease, a low-level alarm will sound when level reaches a predetermined point. The alarm alerts the operator that some action needs to be taken. If, on the other hand, the flow of water from the condensate storage tank to the condenser causes the level in the hot well to return to normal, the signal from the transmitter will increase, closing the level control valve. A similar thing happens in the dump line. If the condenser hot well level begins to increase, the signal from the transmitter to level control valve 1B will increase. This time, control valve LCV1B will begin to open. When it opens, water in the condensate system is redirected to the condensate storage tank. As level in the hot well decreases, the transmitter signal decreases, closing 1B. If this action doesn't return the system to normal, then the high-level alarm will alert the operator to the problem. As you can see from this example, instrumentation is vital for the control of a system such as this. We'll talk about control systems in greater detail in the next segment. For now, though, let's review what we've learned. We learned the instrumentation necessary to operate a condensate system. We saw how this instrumentation is shown on P&IDs and how a basic control system works. Now's a good time to stop so that you can read the material in the text and answer the questions. Remember, if you have any trouble following this material, ask your instructor to help you. Throughout this topic on instrumentation, we've stressed the importance of understanding how instruments operate and the types of information available to you on P&IDs. As you've seen, virtually all vital operations in a plant have some instrumentation associated with them. In this segment, we'll cover the primary reason for having instrumentation: control. As an operator, your job is to control the systems at work in your plant, and you can't do that unless you understand how to use the instrumentation that is a part of every system. By control, we mean any method used to measure and regulate a variable, such as pressure, flow, temperature, and level. The whole idea behind control is to maintain a variable at a desired value or within a certain range. The desired value is usually called the set point. Almost all systems have one or more set points that need to be maintained. In general, methods of control can be broken into two broad categories: manual control and automatic control. With a manual control system, an operator must physically operate a component which affects the system. With an automatic control system, all operations are done by the system itself. For our discussion of control systems, we'll use the condensate system that we looked at in the last segment. We'll show you how level in the feed water storage tank can be controlled manually and automatically. All condensate going to the feed water system passes through this level control valve, LCV11. The deaerator and the storage tank. Throttling LCV11 allows the level in the feed water storage tank to be controlled. Opening the valve increases flow and raises level, while closing the valve reduces condensate flow and lowers the storage tank level. On this manual system, condensate level is sensed by a float device that operates level indicator LI1-11. The plain circle used to identify LI1-11 tells you that the instrument is locally mounted. This simplified diagram of the system we've just discussed will help you understand how manual control of level in the feed water tank works. Here's the level control valve. Here's the deaerator. Here's the storage tank. And here's the float device, which, in a manual control system, operates an indicator. To manually control this system, an operator must keep a constant watch on the level indicator. If level gets too high, the operator must close down the valve to reduce the condensate flow to the storage tank. The system will then return to normal. By the same token, if level gets too low, then the operator must open the valve a few turns to increase flow to the storage tank. By throttling the control valve, the operator can maintain storage tank level within a desired range. One obvious disadvantage of a manual control system is that the operator is required to keep a constant eye on the level indicator and adjust the control valve accordingly. This doesn't give the operator much time to do anything else. An automatic control system helps to eliminate this problem by performing the same operations without the aid of the operator. However, for a feed water storage tank control system to work automatically, 4 additional components must be added: a remote actuator, a transmitter, a comparator, and a set point generator. This is what those components look like on a P&ID. First, to make LCV11 an automatic instead of manual valve, it must be equipped with a remote actuator. A remote actuator is a device which allows a valve to be operated from a remote location. According to our legend, the symbol you see here shows that LCV-11 has been equipped with a pneumatic actuator, making it an air-operated valve. The second thing that we've changed is the level indicator connected to the float device. Instead of simply having a local indicator, we now have a level indicating control transmitter, LICT1-11. The plain circle designates this instrument as being locally mounted. The transmitter is used to send an output signal to the third additional component needed to make this an automatic system, the comparator. A comparator is a device that looks at 2 different input signals, decides which one is larger and by how much. Then it sends out a signal proportional to the difference between the 2 signals. Usually, one of the input signals is a set point, and the other input signal is the variable being controlled, generally referred to as the measured variable. The last component we must add is a set point generator. In our example, the set point is the desired level of feed water in the storage tank, which in this case is 8 feet. A set point generator supplies the comparator with a signal proportional to 8 feet of water. The float device and transmitter measure the actual level of water in the feed water storage tank, and the transmitter sends a signal proportional to the actual level to the comparator. The comparator compares both signals and determines if there is any difference between them. If there is a difference, the comparator generates an error signal that is proportional to the difference between the set point and the measured variable. In this case, the error signal is pneumatic and operates the air-operated control valve LCV11. The signal causes the valve to be repositioned to correct the error. Let's use this illustration of a simplified automatic level control system to see how it works. Here's that air-operated control valve. Here is the comparator. And here is the set point generator. This is the float device. And here's the level indicating control transmitter. Right now, the level in the tank is 8 feet. That's exactly where it should be. The signals to the comparator from the set point generator and the transmitter are the same, so that no error signal is generated. But watch what happens when level increases. As the level in the storage tank increases above 8 feet, the signal from the transmitter also increases. The set point generator signal remains the same. The comparator senses the difference between the two signals and sends a proportional pneumatic signal to the control valve. This signal causes the control valve to close down, reducing the flow of condensate into the tank. Reduced flow causes the level in the storage tank to drop. When the level again reaches 8 feet, the transmitter output decreases. The error signal goes to 0, the control valve opens, and flow increases. Well, now that you know how simple manual and automatic systems work, let's look at the 6 essential elements of control. These elements are the process information, the set point, the error signal, the control device, and feedback. The 6 elements of control can be arranged in a simple diagram to show their interrelationships. First, we have the process that is being controlled. In our example, the process is the storage of feed water. The second element is process information. This usually consists of information about the process variable. In our example, the variable is level, and the information provided is actual level of feed water in the storage tank. The set point is the third element of control. As you know, the set point is the desired value of the variable. In the case of the feed water tank, the desired level or set point is 8 feet of water. The fourth element, the error signal, is generated by comparing the set point with the process information. In the system we just looked at, the error signal is the difference in level between the set point and the actual water level in the storage tank. The error signal operates the fifth element of control, the control device. The control device in our system is the valve which regulates the amount of water reaching the tank. The valve responds to the error signal by opening or closing to readjust condensate flow in relation to the error signal. This adjustment maintains the level in the tank at the set point. The final control element is feedback. Feedback is really nothing more than a way of letting the control system know that what is supposed to happen is happening. Without feedback, the control system wouldn't have any way of knowing how it is affecting the system it's controlling. In a simple control system, like we've been talking about, the process information may also serve as feedback. For example, when an error signal is generated because level in the storage tank is less than 8 feet, the control valve opens to allow more flow of condensate into the tank. This causes level to increase. The level sensor detects this increase and feeds it back to the control system. In this way, the control system sees that level is responding and starts closing the valve so that by the time level has returned to 8 feet, the valve will be back to approximately its original position. Without this feedback, the control system would tend to fluctuate. With these 6 elements, plant systems can be controlled and operated within precise values. Other control systems that you encounter may be more complicated than what you've seen here. However, they will usually have these 6 elements in common. We've gone over a great deal of information in this unit. We've shown you how instrumentation and control systems appear on P&IDs. We've also shown you how P&IDs connect with other P&IDs so that you can trace a system from start to finish. Finally, you've learned about the 6 essential elements of control that are common to almost all control systems. Now is a good time to stop so that you can read the material in the text and answer the questions. Instrumentation is not an easy topic, so if you have any questions about the material that we've covered in this unit, clear them up with your instructor.